University of Dresden. The reason why we're doing it, it shows a little bit that the topics that we have chosen for ComNets 3 are very relevant also for our excellence cluster. And you will see a lot of these kind of adjustments that we are doing for cyber physical systems, for adaptive streaming, for quantum, and all of these things are now boiled together to this one topic. So I don't know if you are sure that whether you have heard about the Tactile Internet. We call it Center for Tactile Internet with human in the loop. So for us, it's very important to understand there are machines which have a control loop, and there are humans which actually also have a control loop, right? So there is also in IEEE a sub-working group that is working on the Tactile Internet, and they have gave it definition, which got improved over the time, and we are also part of that. So we made sure that also our view is in that. And the official definition you can read here, which says a network or a network of networks for remotely accessing, perceiving, manipulating, or controlling real or virtual object or processes in perceived real time by humans or machines. So it's about machines, it's about humans, it's about real time, it's about real or virtual objects and what you can do with that. All of these things are currently discussed here at the Technical University in Dresden. We have also some collaborators in Munich. Technical University of Munich is part of that with 2 professors. We might increase it to even 3. There's in Munich the DLR center which is there, and here in Dresden we also have Fraunhofer involved there. So that is something what the IEEE was looking at it. In the beginning of the Tactile Internet, it was mainly something like, let's make low latency communication, right? And therefore, you always have talked to people from electrical engineering, computer science, and they thought it's something like cyber physical systems on steroids, right? That was the original view. Now you can also see not only by machines, that was the original definition, but now we are talking also about humans. And when humans come into the picture, of course, you can see that we are not talking only with electrical engineering and computer scientists. We also have to talk to medical people, to psychology people, which makes our center a very interdisciplinary approach. So for us, when we want to introduce the Tactile Internet, we always try to tell the people, you know what the Internet is. And the Internet is something where you democratize the access to information for everybody independent of location and time. So when you have internet access, you open a wiki, there's a lot of information over there, right? Compared to 20 years ago, where you had to go to the library, you're taking a book out. So the internet, as it is now, made a really good job in getting access to information. It's not always this high educational information. It can be also some Netflix video whatsoever, but you have a lot of these kind of easy access to information nowadays. And it's not whether you are rich or poor. As long as you have an internet connection, you're part of the big game. Now, the Tactile Internet and what it's aiming for is to democratize the access now to skills and expertise. So before that, it was information. Now we talk about skills and expertise. And skills and expertise, why? We would like to promote equity for people of different genders, ages, cultural backgrounds, or physical limitations. Which means maybe there's a skill you never had, you want to train it, right? Or there's a skill you had, but you lost it because you got older or you had an accident, right? We don't hope that this happens, but the thing is that these things are important now to understand, can we have a skill and train it to humans, or do we have a skill and give it to machines, right? Both sides are possible. Now, we always come from use cases. So in our center, we said, let's look into 3 different working fields. For example, medicine was one thing, industry or Internet of Skills. Medicine is clear, remote operation, training the doctors. Industry is really something that we have looked into extensively from the beginning in Industry 4.0 or industrial internet, as some people call it. And Internet of Skills is really how humans can learn something. Now, I give you an example how you can really convey a skill from a person for example, to a machine, right? The other way is also possible, but let's just look at these conveying a skill to another machine, right? And an expert is for me somebody who can do something very well, right? Like my grandpa working on wood, right? He was an expert on that. He would have difficulties to train his skills to a robot, though, right? If I would come with and say, here's an Xbox controller, he would not even know what it is, right? Even if you know what it is, you have difficulties to understand how to control a robot from an Xbox controller to this kind of things. And if you then want to map your skill on that, it's not so easy, right? You can think about better remote controls. So, for example, here we have one idea. This is the COO of the Deutsche Telekom, who has two sensors in the hand. There's some sensors in his jacket and at his glasses. And whenever you move, right, the humanoid robot that we built, Mr. T, is also moving, right? So this was something we did for the Mobile World Congress in 2017 together with Deutsche Telekom. They used it also for other stuff, right? So very interesting to see. Maybe you don't need an Xbox controller. You can have a more advanced controller. Nevertheless, there's another problem, which is called scalability. Now, if you go to Wikipedia, it doesn't matter if there's one guy looking into Wikipedia or millions. It scales, right? And there's not a human being reading you a book. What we would do here with the skill set. You, for example, you ask, you are good at it. Can you just tell the robot how to do it? Now, how can we do this to scale it, to get it maybe not to one robot, but to millions of robots if somebody is asking for the skill set? Then you can just go and look how it's done today. So if you go to the car manufacturers here in Germany, they have a lot of these robots, right? And they're doing this for millions and millions of cars. And what you would do is you have somebody who has an idea how to build a car, the expert. He has to talk to a computer scientist who will then program the KUKA robot or FANUC robot whatsoever in order to make the robot to do what it is. Once this is done, then you can scale it because you can run it on one robot, on multiple robots, and you can do it over and over and over again. You don't need the expert afterwards. But there are some problems in this thing. For car manufacturers, it's okay because the product, they're building millions of them, and the product itself is very expensive. So doing this whole procedure, as you can see here, is not a problem, even though it costs a lot of money. But now imagine the price of the robots are going down dramatically, right? It's not 100K anymore. Robots nowadays cost 2,000, 3,000 euro, and you have something. Maybe not holding a whole car, but if you would like to equip a lot of offices, a lot of small shops with robots, then it's easy now. So they cost only a little money, but even if it costs little money, they will not do the same job over and over again. So what we would like to achieve, this is the goal of Industry 4.0, to get the lot size. So how many products you do significantly and down. So maybe you do only one product or 2 or 3 products of that. So you need to reprogram the robot over and over again. And then if you understand that the cost currently for the car manufacturers and for the programmer to the robot, even though they're expensive now, is 6 times higher, you can understand that scalability is not easy to achieve with such an approach, and even to make it reprogrammable. So when the robots go down, there's another problem. You need more of these programmers. And we don't have here at Technical University enough people that can program a robot like this, right? So there are now a lot of ways to say, okay, maybe we, instead of programming it, you can show him what to do. That's not very precise. So even in the car manufacturers now, they still program it, right? And the whole process is also timely. So the expert talking to the computer scientist takes a lot of time. And in the end, the expert will give up and say, yeah, the robot is doing more or less what I wanted to do. Not exactly, but it's okay. And this can take months, right? I come back to this time issue. So what we did in Dresden, I think already with the time I came here, there were some people talking about programming the robot in a different way. And the idea was just to say, why don't we take intelligent closing, which means your closing with sensors and actuators. In the first place, we only need sensors. And tell the expert, show me what you can do. Do it multiple times. And when you do it multiple times, it's not that there's an expert looking at you. We don't need the computer scientist anymore. We have some machine learning type that can create the software by itself. So the expert is doing it once. If you do it once, you can maybe smooth out the movements, but in the end you would replay it. But if the expert would do it multiple times, out of these multiple repetition, with machine learning, you can figure out what is the intention, right? What should I do? And at that time, when we also built this Mr. T, there were two ideas, right? One is really to write a proposal for a center of excellence, and nobody tells you whether this will work or not. And at the same time, we created a startup, which here is still located in Dresden. It's called Wandelbots. So one was really focusing on the industrial use case, say, let's do a product. And they said, what kind of research do we need there? And having this in mind, the Wandelbots guys very quickly got attention from the industry. Here's the CEO of Volkswagen, who has a jacket on with sensors on it, right? And he has to place a loudspeaker into the door of his car. And if you would have done this on the classical way, it has taken them months. Therefore, they're choosing this example. Here, the CEO was repeating it 3 times, and afterward, the robot understands. The job was quite simple, right? But nevertheless, if you do it the classical way, it costs a lot of money. Money is not an issue. They have a lot of money, but it costs also time. And now, if you would like to produce even cars that are a little bit different because you want to have a more personal touch on the car, then you need to be able to reprogram the robot a little bit, right? And say there are different activities you can do. So Wandelbots went one way and said, okay, we have a product now, and they're quite successful. If you look it up here in Dresden, if you go to the Großen Garten, they have a villa there with a big sign on this now. There are over 100 people. Very cool company. And you could say, okay, problem solved, right? Not yet, because what they do is teaching the robot in close proximity. So you're always standing next to the robot, right? So with our Center of Excellence, one thing first. Here's one of the first prototypes for Wandelbots. There's a 14-year-old girl. She's teaching the robot some artificial skills, right? So here it is. The human plays a white cylinder, and then she taught the robot to place 2 black ones on top of that in the size has to be larger than the white one we are putting there, right? So the intention is pretty clear. And you see she's also operating on the tablet. The tablet was in the beginning only for starting and stopping the recording. Nowadays, you can even see in 3-dimensional the movement of the robot, go debug the movements and tell the robot go from one stepping point to the next, and then you can see what he's doing and maybe correcting it manually on the tablet, right? So from the industry side, that's pretty cool. But what we need to do in our Center for Excellence is to say, we don't want to teach the robot only if he's next to us. We would like to teach him worldwide, like the World Wide Web, right? Here we have the worldwide programming of robots or a skill exchange. Now, sorry, it's my clock. It will stop from a time I made a mistake by turning it on. So it will come back at 12, and then we have to make a small pause. So if you want to exchange skills globally, what you have to do is you have to perform your skills. So you have this suit, this very cool suit now with a lot of sensors, and you're moving, and while you're moving, all of your movements, all the sensors will grab and send it over wherever the robot, for example, is now. But in order to teach it very well, what you need is feedback. We call it a multimodal feedback. So you would like to see what's going on there, right? Maybe you want to react on something that goes there. Maybe you need also some audio to see or hear whether it's going right or wrong what you're doing. And the best would be if you also get a tactile, a haptic feedback. So with the Mr. T, I was able to put on the virtual glasses and operate from the distance. that was quite interesting. And we had the Mr. T had a real hand, right? And if you want to grab a cup of tea or coffee, which is pretty easy job, you might say, but when you are missing the tactile haptic feedback, you're always bumping into the mug, and then sometimes you hear it and you stop, right? And then there's a little bit of latency. It was pretty hard to really grab over distance a cup of coffee. Having the kind of feedback haptic and tactile, what you also would need is not only sensors, you need actuators, maybe in a glove where you can feel what's going on, right? When you touch something physically on the remote side, you want to feel it on your side. So when you want to send the skills and get a multimodal feedback where it's a control loop, right? And in order to make this real-time feeling, what you have to deal is, wait a minute, I have to go to the other side. You have to look into the different modalities, right? The different senses. And if you compare tactile, audio, and video, and if you map it to a communication network, you will say, there is something very interesting because they're different in the data rate. So we all learned that video is big data, right? Audio, not so much. Even high quality audio compared to video is nothing, right? So what we would say medium to low data rate. And what is with haptic? So if you have 1,000 sensors in your hand or on your body whatsoever, is this a lot of data rate? Is this little data rate? So for audio and video, we have something what is called source compression, that you can compress the data. With haptic, we don't have it yet. There are some attempts, but it's not very standardized. They're not so good. It depends on the task you're doing. Like also video compression depends on the content you're feeding into your compressor, right? So data rate wise, there's something in it. But these modalities are also different in not only in data rate, also in the latency requirements. What does it mean? So here comes in the psychology people, and they will tell you how sensible we are when we have latency, right? So I give you an example. This is a human being, right, that would like to grab the ball. And what we do with the camera on top of this Samsung gear, we can delay the reality. And what we are doing is we are delaying it by LTE latency and duplicating by 2 times. Why? Because your signal has to go to one side and come back, right? If the other side would have latency, then you have to have it 4 times, right? So you see that people have a difficulty in an LTE environment to get the ball. So latency is quite annoying when you want to act in augmented or in virtual realities, right? And this was just to blame 4G and say, hey, you're not fast enough, right? But if latency is important to people, what and how are we sensitive? And here you see a distribution telling you how the time requirements are, for example, for visual, right? Some of the stuff can be 100 of milliseconds, but we are also sensible for 15 milliseconds. And I was wondering, why is this, right? I mean, if we do video conferencing, a little bit of delay, we can digest that. So why is this 15 milliseconds? That depends where it happens, right? If it happens in front of you or at the side view. And it seems that with the side view, we don't see so much information, but we are very sensible what happens there. And that is because some 1,000 years ago, when the animals wanted to kill us, they always came from the side or from the back, never from the front, right? And in the front, we are not so delay sensitive, but we get a lot of data rate from your eye. And on the side, there's not so much data rate, but there's a lot of sensibility. So it also depends from person to person, right? It depends on aging, right? If you're very old, you're not so sensitive anymore as if you're young. In audio, the same, right? So some people are very sensible, like 3 milliseconds. We know about this number so well because Sennheiser in Hanover, which do the headsets, they told us about the 3 milliseconds. If you have a professional musician, and the time where he's touching his instrument and the sound is coming to his ear is more than 3 milliseconds, he will understand that there's a problem. Yeah? And they call it the absolute hearing, right? If you're a musician, you might have it, right? If you want to control your guitar and you can do this without, or you want to tune it, you can do it without a machine, then you have the absolute hearing. I don't have it. So maybe I'm more on the right, 5 milliseconds, 10 milliseconds. The older I get, even this will process. So aging seems to be a crucial thing there. But there's something else, which is tactile, which most of the times is 1 millisecond. So if you touch something and you don't get feedback in 1 millisecond, it doesn't seem to be your, it doesn't seem to be a real environment. Now, it's very interesting because if you know something about the data that flows from the touch over your arm, then you will say, that's strange, right? The speed here is not fast enough to get this into 1 millisecond into your brain. First of all, it's not putting it always into your brain. There are other things like stomach and the back of your body where something in the spine what might be also connected to the brain. Don't ask me, I'm not a medical guy here, but it is processed somewhere else, right? The concept of mobile edge cloud, where you bring something closer to where it happens, that seems to be in the body as well. Otherwise, a goalkeeper could not have this reaction time that you sometimes see. The other thing is, there is a pre-processing from your brain and your eye. So if I want to touch something and I feel that, for example, I have to do it here. I want to touch the pen. I know that I will touch the pen, right? So somebody's preloading this kind of touch maybe into my brain. It's interesting because if you touch something hot, that you, not like a fire that you see, but if you have a pen which looks normal, could be cold, could be hot, and you touch it, you see that there's always a lot of delay in it because this is actually processing by your arm and getting here and say, oh, hot. You cannot see it, right? But if it's already so hot that it's reddish and you see, oh, it will be hot, then you get the information faster. That's quite an interesting aspect. We have to work on this. When you see the plot, it comes from a paper from the psychology people, then you will see, okay, very interesting curves. But if you look at the y-axis, it's called fraction of rats. So it's made for rats, not for humans. Psychology people and medical people tell us rats and humans are the same. So for that, for this kind of investigation, it can be. But here in the extents cluster, we are now performing such curves now also with real humans. It's not so easy. You need a lot of equipment without opening the head this time, right? Good. So you see there are very stiff requirements, right? 1 and 3 milliseconds is tough. Even 15 milliseconds can be tough for high data rate. But now you have this tuple, right? Data rate and latency. And if you remember ComNets 2, what we discussed is the trade-off. There's always a trade-off. Either you have good throughput or you have good latency, but not both at the same time if you not want to use much of your frequency or your resources in general. So what can we do here, right? First of all, we have one problem. Speed of light. What does it mean? Your signal travels 300 kilometers in 1 millisecond. That sounds very fast. The problem is, if you think about a global tactile internet, not so much. So if I would like to train a robot in Japan, these are 9,000 kilometers, more or less, then you see 30 milliseconds. And this is far beyond everything that you have seen in the plot before. So how can you really get this done? How can you train a robot on the other side? So currently, you would take the expert, fly him to Japan, he stands next to the robot, not a problem, because he's in close proximity. But if you stay in Germany and you want to teach him, you get an extra delay, right? 30 milliseconds is more or less what LTE was in our example before. Now, let's have a look at this kind of 1 millisecond, right? If this is the hard bound, where could we spend it? And here you see three main parts, or let's say it's that two parts. I call it the mobile part and the fixed part. And then we say 40% goes to the mobile part, 60% in the fixed part. So that's quite interesting. And if you look at the sensors and actuators, I always want to have end-to-end, right? So you go from the sensor, like a light switch, you press, and then the bulb goes on. That's a very easy sensor-actuator pair. Could also be I have a glove with many sensors on it, and I do something, and the actuator is a hand, mechanical hand. And then if you only give 20% to that, that's not so much. For a light switch, it would be enough, but 20 milliseconds, especially because this is a mass market. So currently, for example, your display is very slow, right? Your cameras are very slow. If we do something nowadays with cameras, we do cameras that have very high frame rates. So, and we don't allow them to compress the data. We say, don't compress, because compressing will mean, this means a lot of latency. Just send us the data. It's high data rate, but most test beds that we have, they can digest it. But compression is counterproductive for latency. Then you come to the wireless link, because most things are connected wirelessly. In 5G, we have discussed this also in ComNets too. They talk about millisecond latency, but also sub-millisecond currently for newer releases. So all in all, 40% goes to this side. Then you have 60% of your millisecond on the other side. And what does it mean? I told you 300 kilobit per millisecond. If you spend 25% of the millisecond in transporting it over a fiber, then you have a maximum distance between a possible computing within the network and back, which is 25 kilometers, not more than that. So Japan, don't see that. But then you have something there which is not only a network, now you have a computerized network where something happens within the network. Why is this needed? You can say, why not just forwarding the information? Yeah, you can do it. But imagine you have a company site with 1,000 people working there, and every person has 50 sensors. And if you want to always transport all the data, then the data rate in the network will be so big that it will create problems with your latency. So somewhere you have to compress the data. Either you do it on the sensor itself with embedding computing, or within the network. You cannot compress it all at the sensor side, because you don't know at the sensor side which information will be relevant. The network knows better than maybe the sensor what could be relevant in a certain complex application type, also application dependent. Sometimes you just want to know where are the person currently, that we don't harm them with the robot. But if the human is interacting with the robot very close, then you would like to have give me all the data. We cannot harm not even a finger of him, right? So this is the current setup, right? We have only 35% of our millisecond for calculating something. And this is not so easy. Let me come back to the slides that we discussed in the last lecture. I don't know how to do this. Maybe I do one. Yeah, wonderful. So I'll just go through it, sorry. When we discussed about these plots, I hope you remember that. When we said, okay, there's propagation delay, there's the data rate delay, so the message conveying delay, and the computing delay, right? So what we do is, with 5G, data rate is not a problem, right? It's high, and a packet that comes, for example, from a robot, that a robot is sending out, a Cougar robot, there are only 40 bytes. If you say 10 gigabit per second, 40 bytes, we are talking here about 30 nanoseconds, something around this, 32 nanoseconds, I think. Now, this is very small, but the propagation delay, as I said before, 1 millisecond for 300 kilometers, right? And you have this twice. And the computing can be big. So how can we then get this kind of computing delay down? And the propagation delay we get down by doing this kind of mobile edge cloud idea, moving it up, right? Okay. Having this in mind, I have to go back, sorry, to our slides. We were at 60 something. So have this in mind, latency, how to get it down, right? Now, the reason why we also need the computing is not only to do some filtering, compression in the network with the sensor data. When you want to teach a robot in Japan, and you know it's a Fanuc robot or a KUKA robot. If it's Japan, it's Fanuc most of the times. What you could create is a model. You could create a model of a robot and just bring this model in a virtual form, in a mobile edge cloud, very close to the expert. So he would interact not with a real robot, but with a model of the robot, teaching him something, okay? And it can also be that the robot is doing something in Japan at the same time, but with a delayed action so that you see the outcome. But the expert would interact only with the model of the robot. And because you can get this closer to the expert with the mobile edge cloud approach, the propagation delay is going down, right? That means the model has to run within this 25 kilometer range. The closer it is, the better, but 25 kilometers, let's say, this is the range where the computing has to take place. That is the easy part. And if you come here and want to visit this, we have here something what we call the digital twin demo, where you really can try yourself teaching a robot in a virtual robot in front of you. You only see it virtually, but next to you, there's a real robot doing exactly what you did. And people can give the real robot objects that you will see them and say what to do with that, right? So this is not really a problem. The problem is more if the robot is in an environment there, for example, there are 2 or 3 robots with different teachers, then it's not good that I bring the model of the robot to the expert, because he does not know what they're doing in dependency of the other robots. Maybe we have to create a model of the human and move it towards the robot. And now it becomes complicated because a robot has a technical specifications, humans don't have it. Good news is humans are not as different as we think, but they differ in age. They also differ how tired they are and not. So there is something in it that to create these human models, that is a part of our research currently. Good. I told you that we don't only need to train a skill to a machine. How can we train skills to humans, right? I took here a robot that teaches a human. Not necessarily like this. What it is more the cloud teach the human something. And for that, it's even more important that the suit that we have does not only have sensors or actuators that gives you a little bit feeling of touch. It also should move. The whole jacket should, like an exoskeleton, but not as big, please, right? The whole clothing should be able to move your hand. Currently, we have some experts here at Dresden that are doing that. They can already move the glove, but not very fast, right? They're doing it with piezos. But let's assume we could do this. If you could do that, now imagine you're an old guy that has a dislocated shoulder. And in order to get it done, if you're older, you need a lot of training for that. So what you will do is you go to your car, you drive half an hour to the doctor, you wait 45 minutes in the waiting room, then the doctor will come to you and you do 30 minutes together, and then you go back home. But everybody knows if you do it 8 times a day, it would be better. So either you sit there in the waiting room for the whole day and get your 8 trainings, or we do it virtually. And virtually we mean the patient, the old guy at home, puts on a jacket and the doctor puts on a jacket. The patient calls the doctor says, how are we today? And then the doctor will take over the movement of the jacket, right? So the doctor had only sensors and the patient has the actuators. And by remotely moving the jacket, he can show him some exercises, asking him how he feels, if it hurts, if he can bend a little bit further. And after that, when they have understood what can be done, the doctor will say, please repeat this 20 times. We will see in the next hour. So the whole thing maybe takes 3 to 5 minutes, but the doctor can now jump from patient to patient and we can repeat it over the day, maybe the 8 times. right? So this is something, it's not really a skill, it's more the skill from the doctor that is then brought to the patient. But there are other stuff that we are currently doing, right? For example, training the Olympic team in rowing, right? Or training people to climb. So bouldering is very interesting for our PhD students currently, right? And you could use such a thing, what he has on the arm. It's this is a mock-up currently, right? But they're building it. You can see it now, where you then can either tell him where to go or restricting him not to take the easy route. Currently in bouldering, they are having different routes and they make it different difficulties. Just this closing could make it more difficult because you cannot reach it. Okay. There are other examples. I did not bring it today. For example, in dancing, there was a really cool demonstrations when we had the city truck, where you could see that a professional dancer had some sensors at the body, and it's not training him the whole dance. It's just helping him to run his activity through to learn faster, which means it will tell you now to the left, now to the right. And it's like you have a poem, right? You remember when you had to learn a poem? Maybe you didn't have to learn poems. I had. And it's easier if your mom is always giving you the first word, like the initiative of the sentence, right? First word, and then you remember it. And if you always get the first word, then you go through it, you get more confident. And afterwards, you don't need the first word anymore, right? Every second word and whatsoever. Good. There are a lot of more examples. Also, you can see them here. If you go to the CT.1 webpage, there you can see also more of that. Very interesting. Now, in the end, what we would like to achieve is not only unidirectional learning. We would like to see something like human-machine cohabitation, where humans interact with machines, machines interact with machines. So also an interesting question is, can one machine teach another machine what to do? And this is easy if you're the same robot in the same environment with the same task, you just give him the program. But what if you're not the same robot? What if the task is slightly different or the environment is different? Can a machine teach the other side, right? Also there, Wandelbots did something very nice with the, if you look up the trace pen demonstration they have, it's very interesting how one robot can teach the other robot what to do, cracking the barrier from, for example, from KUKA to FANUC. Normally, you cannot exchange programs like this between these two companies, but with a little trick, you can do it now. So this cohabitation is quite interesting. And here's a nice demo we did a year ago, exactly a year ago. We had the bold guy, I don't even know, he's the CEO of Microsoft, Satya. And he had a trace pan, so not a closing now, it's a tool. And he was teaching something. And while he was teaching this in Seattle, actually the robot in Dresden was training, and he was performing whatever we trained him in Seattle. So there's something about this mobile edge cloud that already works, apparently. Okay, so for us as a center, it's very important to have impact, right? We would like to create impact on research. I will tell you a little bit more about this, where we see that. Of course, we will have, with such an approach, impact on business, right? We are cracking down the time how to program a robot. We make the cost going down to program a robot. So reprogrammability is interesting for small shops. They maybe can afford one robot, but the robot should be trained for new stuff very quickly. And it should be very easy. We should democratize this kind of programming skill to everybody. It's not programming anymore. It's just showcasing it, demonstrating it, and the robot will learn it. And when you have first product with that, of course, you have also impact on society, right? You have impact on the business side, which is also impact on society. But the way how we learn young kids how to do something is maybe different from the way we learned in school. There's something what we try to learn to do here at the university, because we did it at MIT, we did it in Aalborg, in Scandinavian areas, problem-based learning. If your brain tries something out, it learns the stuff faster than if I tell you what to do. If I tell you to do A, B, C, you will say, I got it, but you don't really got it. When you find out yourself that you have to do A, C, then B, A, B, C, that is something where there's a different part of the brain that learns. And this brain is faster. So that motivates a little bit our theory that matters approach. Hands-on is important. But you also, students, you have to understand it. If you don't do this stuff, if you don't failure is a very important stuff for learning, then we will have problems really getting you all of these complex stuff in it, right? So I hope that you buy the business and the society part. I will now talk a little bit about the research part, right? And the whole Center for Tactile Internet here at TU Dresden, we are building it like in virtual research rooms. So you can imagine a real room where people are sitting and working together. But as we are interdisciplinary, we have the task to bring people from different disciplinaries together. And we could place them in the same room and just make them to talk to each other. That was also our plan. But unfortunately, the building process at the university is not as fast as we would need it. Then we said, okay, what can we do? And you see here 3 floors, right? The bottom floor, middle floor, and the high floor. The high floor, I exactly the use case that I showed you before. Medicine, industry, Internet of Skills. And these people tell us what they need from us. So they showcase what they want to do. For example, the medical people said, we want to train our young doctors. And currently it works like this. The operator, the professor, is operating the human body, and there are cameras. And people are sitting in the next room looking what he's doing. But as soon as he's opening the body of the person and is going in with the hands into the blood, you only see he is in the body. But what is he doing? And it would be great if the students would have some gloves. The professor would have some gloves. And while he's performing something, your hands are also moving. And maybe you can even feel the touch, what he's feeling. Why is this important? For cancer operations, they want to find out where is the meat that is hard and which one is soft. So hard means cancer. You have to cut it out. And the soft one, you can leave it. But what is soft, what is hard? There is the skill set of the professor. And if you want to teach it to the students, they need some gloves that are really good. They have these touch feelings, right? And industry and the other rooms, they have requirements. They bring it down. And let me go to the bottom now. What are in the bottom? In the bottom, we have really the experts. These could be, there's no interdisciplinary research there at all. These are the experts that do research on psychology and medical. This is TP1, humans. TP2 is working on sensors and actuators, how to build them, right? TP4 is doing flexible electronics. So if you want to include it into the closing, you need flexible electronics that is not consuming a lot of energy. And then you have TP3 that do new information theory, how to convey data and compress data. And TP5 is then tactile computing, where to perform, where's privacy issues. So TP5 is more computer scientist. TP3, electrical engineering. TP4, TP2, also electrical engineering maybe. And TP1, psychology and medicine, you might say. But now, if I, for example, would create a new theorem on information theory, the U rooms cannot use it. So we have the enabling rooms, the K rooms, the key technology rooms, where people from different rooms come together. So K1 is actually doing or looking at the problem I was describing before, where they said, let's have a codec that can compress the haptic codes. By the way, soon my clock will make ding dong, then I have a short pause for you. Now, you get 10 seconds. Listen to the nice voice. 12 times. Bravo. So in K1, as I said, haptic codes, how can we compress the data rate of haptic information, right? In order to compress something, you need to know something about correlation, right? In video, you want to understand how the macro blocks are depending on each other, what has changed, etc. pp. In audio, the same, right? So in haptic, you would like to understand correlation. And the nice thing is about what is the correlation? You know about correlation of the data if you know the human body. So TP1, there are people from TP1 in K1 telling the people what is the correlation. For example, if you look at the finger, right? It's if you do like this, you cannot do. There are three elements, right? But you cannot control them individually. You pull one, and it's like a string. If you know the correlation, that's nice. But there are also other correlations like this, right? And if you even understand the task set, that's interesting. TP3 has then the methods how to compress, right? And TP4 and TP2 will tell you what kind of sensor data you might expect there. You can even say, I would like to have all the data, but if you have all the data, that means you have to compress a lot. Can you have a subset of the data already? So they're all discussing it, right? K2, intelligent networks, is of course bringing the other use cases, saying, what do you need? Yeah, we need a network like body area network, a network that works over the body alone, or local area network, or wide area networks, right? Between here and Munich, the Deutsche Telekom is helping us there. In order to get the intelligent network done, TP5 is there, TP3 is there, and also TP4, because they have, for their flexible electronics, they have a body hub, they call it. So computing at the human body itself. Then K3 is augmented PI, where we bring together sensors and actuators together with the flexible electronics. And core adaptation is the way how we learn. There's TP5, there's TP3, understanding how machine learning works, right? And also TP1. And what you see is the higher you get in the building, the more interdisciplinary work is there. In the U rooms, you will find all the disciplines in one room, right, talking to each other. So rooms are for us a very suitable way. We like them in order to classify our research. Over the 7 years that we have, we will maybe create new rooms or remodel rooms that exist, or even close down rooms if you think, oh, this research stuff is done. But in all of the rooms, something happens, right? And let me guide you through. So the U rooms, you heard about this, medicine, industry, internet skills. K1, I told you already, data reduction for efficient communication. It's very important, for example, for the operation room. There are a lot of actuators, there are a lot of sensors, and how to bring these sensors also together with the sensor data of the humans. That is also interesting. TP2, again, multimodal variables with ultra low latency sensing and very high resolutions. And what you see here is also how we build these rooms on top of each other. So the U1 room will say, I need K1 for sure, right? And K1 will say, I need TP2 for that, right? Ultra small bandable electronics, right? And U1 will also say, I need K4, right? Models that capture intention and actions. So currently we are building a robot that should help a professional doctor while operating by looking up what kind of tools he will need in the next step, right? So the intention and actions that define a surgical task, that should be known to the machine to understand, now I will give you tool B or C, right? And in order to have K4 done in the right way, you need a good understanding of TP1, right? And maybe TP5, etc. pp. So you see, they are always built on top of each other. That's the way how the flow goes. Here are some slides about the interdisciplinary approach. We have 8 PIs, so in all the center has 25 PIs. 8 PIs are in the electrical engineering, 8 in computer science, 4 from psychology, 2 from medicine, and 2 from mechanical engineering, right? And externals, we are, as I said, Fraunhofer and also DLR is there. Then we always have some cooperation with other universities like Arizona State University, MIT is there, University of California, San Francisco. We have industry partners like Wandelbots or Deutsche Telekom. And then you see also the interaction about our PIs that you see here. Maybe some of the professors you already have seen in your curriculum. We do always some general assemblies where we all got together to foster this kind of uh, collaborative work, because interdisciplinary work is not so easy, right? Because I, as an engineer, have to talk with somebody from psychology. That needs to be trained. I think we did a pretty good job so far already writing the proposal, but over the last 2 years, there's also done something. Now, inside our pyramid, if you look at this, we also created a lot of startups lately that are helping us to do the research in the area, but also to see how the products perform in the real world. Wandelbots, you have heard about it. They are more in the industry space. Inari, they are doing clothing for surfing, right? To help people how to do the right surfing, to get equilibrium, to learn faster. Mimetic is building up a nice glove with a lot of information, processing the data, trying to get low latency up to negative latency. We have people like Campus Genius and Meshmerize. They are more in the intelligent networks, creating 5G networks or meshed networks. So also companies, if you want to do something with them in your master's student thesis, maybe something interesting. We also have other activities aligned with the with our city activity, the Center for AI, the Schaufler-led Foundation, with the opening is today. They have 9 PhDs for 10 years. No, 10 PhDs for 9 years, where they are looking into artificial intelligence and ethical questions. So this is not our part. That will be done in a totally new center, right? Very good for us. We also got a new project, 50 million for the Else Kröner-Fresenius Stiftung, where we look into robots, machine learning inside the clinic. So actually inside the clinic is one new project doing that. And then we have something like the 5G campus project that is doing campus, but it's helping us also in city to bring these kind of use cases to the countryside. These are the books that we doing there. And the first 2 years, you can see, have a direct city context. The third one, not yet. I will come to that. Quantum communication, that's the one that plays a bigger role later. And if you see, the Tactile Internet has involved all 12 rooms. The computing there is TP3, TP5, and K2. That was working on this book. And quantum is TP3 and K2. That is the address room where quantum will play a role later more. To create this kind of impact on society, we also have a collaboration with the Gymnasium Pieschen here in Dresden, where we get some of our results already addressed there. They have a robot from us where they can also try out the teaching of robots there. In the plan was also to have a nice truck where we can go from school to teach possible young researchers about our topic. And this is very important for us because we believe that if we want to have people interested, especially females, into the kind of math, computer scientists, they don't like it so much because they like more the part where they can take care of people. And now with CT, you get both, right? You have people there, take care of people, but you see it's important to also have math and computer science there. And maybe they will go for STEM content instead of avoiding the STEM content, right? Unfortunately, we never got this truck funded because there was a reduction in the payment for all projects in Germany, and we had to get loose some of the stuff that maybe we don't need right away. Nevertheless, what we did is we showcased this last summer. There was a truck here at the Postplatz. It was a big truck where we had the possibility here, also Lange nach der Wissenschaft, where we invited people to visit our research. This was the inside of the truck. We had some robots, as you can see, a lot of different nations telling this to the people of Dresden. Hey, we are so diverse, even in the people that we are working here. We was also, as you see, the cylinders. They could really try that. There was a robot making selfies. So we engaged quite well with the people, but especially with the young talents, right? Here you see Herero giving a talk, and you see the same slide that you have seen before. So they don't see the whole slide deck, but they see some of the slides that you have seen here. And you see already a graph here. It was the very first graph. You see the sensors, they're in waved, right? This is a resistor, and you can just do like this, and then we can compute how your hand is doing. There are some downsides with this very cheap approach, and you see the computing is on top of it. Battery comes from the outside. Nowadays, everything is becoming very small. If you go now to Mimetic and ask them for a demonstration, very interesting. Good. This is the campus that I was talking about. So here you see a 5G communication network with mobile edge cloud in the back, where we can teach the robot to do something, what he's doing here. So one example first, that was where we went to a small bakery in Görlitz. So you see here one guy from Wandelbots training the robot how to take something from the what is this called, from the plate, and organizing it. They have a gripper for that made, right, very nicely. So in one day we helped the bakery guy who has never ever programmed in his life. He has still a feature phone, not even a smartphone. But he was able to engage him that we could do something with him and show him how easy it is to program something. Now, in the near future, the rooms that we have, as I said, we will remodel them a little bit. We will extend them. We will close them down maybe. And there will be new professorships coming. For example, we talk about new materials. So currently we do everything with materials we know, but there are some materials like graphene, right? Maybe we can use them to get better sensors, better connectors. We would like to have also one field of social effective touch. So touch is so important. Maybe we make an own room of touch. And the one of quantum and post-channel that you also have heard before will also enrich the K2 and the TP3 room. And there might be a new room for entertainment and care. Gaming was always on our list. In the beginning, we did not like to put it there because we thought maybe they don't take us serious, right? But when we defended it, there were some people standing up, why don't you have gaming? Because the gamers are the ones that always know about latency. So because now they ask us to do it, there will be also a whole new room talking about what about gaming, right? We were hiding gaming in the Internet of Skills, but maybe we can do our own room. And currently we have one PhD. She's doing something like how to solve Rubik's Magic and train people how to do it. So you have a glove and you can see the movements instead of having sensors inside the Rubik Magic or cameras. You just have it with your fingers, because if you have one camera and you do it in the bottom with a pinky finger, right, to do this trick to be faster, then the camera might not see it. Right, and sensors inside require sensors in all of the toys. Why not just having it at the glove? And if you want to see there a demo, I hope that this year still we have a demo on the Rubik's Magic. Good. Talking about the rooms, this is the new building they want to do on campus. Maybe in the next years, we will have such a building for us where we also have real rooms where we can map the virtual research room directly into physical rooms. Okay, this is the team that made the proposal and was quite happy to get it funded, right? Okay, that was my introduction to the tactile internet. Again, not so much interaction. Nevertheless, if you have questions now, it's your time to have some questions. As long as nobody typing, let me just recap what my intention was, right? In the last lecture, we talked about quantum will be important, post-channel might be important, molecular might be important, all these topics. And you might say, why are they really important or not? But you should see that even though some of them are maybe become relevant in 5 years, 6 years, it's good for you that you have leverage in your future career, right? And that you see that we are also not only preaching something, we are eating our own dog food, right? We know that what we are doing there in research, we also want to use somewhere, and we do it in our own research, flagship research projects. But we also do this to create new companies, right? And I would say by end of the year, next year, there will be also one company in the area of quantum. Okay, if there are no questions directly to the topic, then I would like to thank you for coming back. I see we are 20 people again, like yesterday. So that seems that I did not annoy you too much yesterday. Next lecture will be given by Johannes and Peter. Peter have set already up everything on the web for you, also the discussion room. Next week I will not be even here in Dresden, but I will be also listening in. I'm also very curious what they have prepared for you for the cyber physical systems. So this is, you get a cyber physical system and you should train it and see how communication and latency has an impact on the machines. Maybe, Ricardo, we make a note that maybe the people can also visit the room of the psychology people where they measure the latency of the humans. That could be something very interesting. Maybe once they are here, we can give them a walkthrough.
Okay, yeah.
Yeah. Can you put this on the link? As you see, we are trying to enrich the content of the lecture on the fly. That shows you how relevant the research is and what we can do there. Okay, then I don't want to steal your time. Thank you very much. It was a pleasure having you, even though I cannot see you. That's a pity. But we will see us maybe when you do the hands-on session, then I will say hello. Every time I have the chance, I will come by and say hello with a mask. So have a nice one. Bye-bye.